Hi there. So in my last couple of videos, I talked about the product and the quotient rule, how we could take the derivative of functions when they're multiplying or dividing into each other. Okay, so kind of some tools to add to your toolkit for differentiation, right? Now I'm going to be talking about the chain rule. So the chain rule has a bunch of applications just like the product rule and the quotient rule, and you typically need to use it when you're dealing with composite functions, so maybe sine of 2x or tangent of 5x, or also when you're dealing with functions that have lots of powers in them. Okay, so maybe you're taking a polynomial to the power of 5 or something like that. Okay, so what is the chain rule? Well, when we have a function, okay, let's say we have y equals sine x, right? Um, x is the inside, like the thing that's being composed within the function, right? But if we take the derivative of sine x, we have y prime. That's going to equal cosine x, right? Because we know that the derivative of sine x with respect to x is just cos x. But what happens when we have, let's say we're taking the derivative of sine of 2x. So y equals sine 2x. Well, now what do we do? Well, when it was just sine x, the inside of the function was just 2x, right? So we just had to take the derivative of sine of x, which was just cosine of x. The chain rule, it's really similar. You take the derivative of the whole thing as if you normally would. So you'd say it was cosine of whatever this inside piece is. So it's going to be cosine of 2x. But you now have to multiply that by the derivative of the inside. So whatever you're calling your inside, you have to keep in mind that you have to multiply your result, right? In this case, it was cosine of 2x by that derivative. So the derivative of 2x is just 2. So the derivative of sine of 2x is just 2 cosine 2x. And you might be thinking, well, how come we don't have to do that when it's just sine of x? Well, actually you do, okay? Because when it's y equals sine x, right, x is your inside. So the derivative of that is just going to be cosine of x times the derivative of your inside. So times dx by dx. Well, dx by dx is just 1. So this is gone, and you're just left with cosine of x. So whenever like your inside is just x, you don't even need the chain rule because you're just multiplying by 1 and it's redundant. Doesn't make a whole lot of sense, but like I said in the examples before, it's going to be useful when you're dealing with composite functions where this isn't an x anymore, right? This could be a 2x, or it's composed of multiple functions, or you're raising it to a big power. So let's just do a couple examples where the chain rule is necessary and you're not going to be able to solve it with your typical table or product or quotient rules, all right? So let's say we're taking the derivative with respect to x, okay, of x squared minus 2x to the power of 6. Okay, so anytime you have a question like this set up, you always think of whatever's in the brackets as your inside. Okay, so for the trig functions with the cosine and the sine, your inside was what's in these brackets. Okay, for polynomials, your inside is what's in these brackets. So the 6 is kind of hanging on the outside. Your inside is going to be x squared minus 2x. So we're going to treat this x squared minus 2x as if it's one thing. Okay, so if we had something to the power of 6, how could we differentiate that? Well, we would bring the 6 out front, and we would lower this exponent by 1. Okay, so let's do that. This is going to equal, our inside is still x squared minus 2x. Okay, except now we brought the 6 out to the front. So it's going to be 6 times your entire inside. Okay, and now we have to lower the exponent by 1, so it's going to be 5 now. Except we're not done, because we still have to multiply by the inside. That's what the chain rule is doing. So we have to multiply by 2x minus 2. Okay, so your answer is going to be 12x, right? Because these are two brackets, we're multiplying it by that. So it's going to be 12x times x squared minus 2x, right? That's the 2x distributing into the bracket on the left there. And then we're going to subtract 12 times x squared minus 2x. And we could factor out the 12, do whatever we want. But that's kind of the main idea there. Okay, and we could also solve this problem by multiplying x squared minus 2x by itself 6 times, because that's really what taking something to the power of 6 is really doing, and we would get the exact same answer. Except it would probably take you about 20 minutes to expand all this out and then take the derivative of each individual thing, and no one likes to do that. So the chain rule is a really quick way of seeing a function that you're differentiating and recognizing that there's a inside that you can decipher that's being raised to the power of something, or you're composing a function and you can differentiate it as if the inside was one thing, and then you multiply it by the derivative of the inside, okay? And one thing I also want to say is, similar to when we were taking the derivative of sine of x, if we were taking the derivative in that last question, it was the inside to the power of 6. So I'll keep that kind of theme. I'll go the derivative of x to the 6. When we use the power rule, we're actually using the chain rule as well, because x is our inside in this case. The chain rule says, okay, treat this x as one thing, so we can bring the 6 out to the front. It's going to be x to the 5th. Remember, we have to multiply by the derivative of the inside, so dx by dx. Well, dx by dx is 1, so it's just going to be 6x to the 5th. And obviously, like with the power rule, if you're differentiating x to the 6th, it's going to be 6x to the 5th. We just know that, but that's only because the inside is x. There's nothing else on the inside. If this was like x squared plus x, our answer wouldn't be 6x squared plus x to the 5th. We would have to multiply it by the derivative of x squared plus x, okay? So that is kind of one example on why it's necessary to use the chain rule. Okay, let's do another one. Let's do the derivative with respect to x of, actually, let's get rid of the brackets, the natural log to the 9th of x. Okay, how could we solve this? Well, this notation here, when the 9 is between the natural log and the x, that really means we're taking the derivative of the natural log of x all to the power of 9. Okay, so just like in the last question, if we have something inside brackets raised to the power of something, we're going to treat this ln x, the thing that's on the inside, as one thing. So if ln x was just like x, say, for example, we would bring this 9 out front and lower the exponent by 1. Okay, so let's do that. This is going to equal 9 times ln x to the power of 8, right? 9 minus 1, but we have to multiply it by the derivative of the inside, because remember, this inside is an x, it's the natural log of x. So it's going to be times 1 over x. Remember, d by dx of ln x is 1 over x. So this is going to be 9 ln to the 8th x over x. Okay, that's going to be your answer there. Let's do another one. Let's do a composite function question. So let's say we're finding the derivative of sine composed of tan composed of x to the 3rd. Okay, Let's say we're finding the derivative of this. How could we do that? Well, remember, we have to treat the stuff inside the brackets as one thing. So right now, let's just call tan of x to the cubed that thing. Okay, so if it was just sine of x, what would the derivative of this be? Well, it would be cosine of x. Okay, so it would be cosine of this inside thing right here. So cosine of tan of x cubed. Okay, but the chain rule says we have to multiply this first thing by the derivative of the inside. Well, right now our inside is tan of x to the 3. So the derivative of tan of x to the 3 is going to be secant squared of x to the 3. It's an ugly e there. Secant squared of x to the 3. And we have to use the chain rule again because this x to the 3 isn't just x. So if we're differentiating tan of x to the 3, we're going to treat this x cubed as if it's one thing, as if it's just x. So secant squared of x cubed times the derivative of x cubed, so times 3x squared. So your answer is going to be 3x squared cos tan x cubed times secant squared of x cubed. Okay, so for this question, the function was composed of tan of x cubed. So there's multiple things going on. This is like h of f of g. Like there's multiple things going on, so we had to apply the chain rule twice here. All right, let's just do one more question. So let's do d by dx of x minus 4 divided by 3 plus 6x, okay, to the power of 5. Whoa, okay, so we have a polynomial divided by a polynomial to the power of 5. Okay, so what does the chain rule tell us? The chain rule tells us that we have to treat the inside like an x. We have to treat it like one thing. So if we treated it like one thing, we would bring this exponent out to the front and lower its value by 1. So it's going to be 5 times whatever our inside is. In this case, it's x minus 4 over 3 plus 6x. Lower the exponent by 4, or by 1, so it's just 4 now. Right, and now we have to multiply this by d by dx, right? The derivative of the inside. So the derivative of x minus 4 over 3 plus 6x. So the first part, we have that covered. It's going to be 5 times x minus 4 over 3 plus 6x to the fourth. Now we're multiplying it by the derivative of a quotient. How do we find the derivative of a quotient? Well, in my last video, I talked about using the quotient rule. So if we have two functions, x minus 4 being divided by 3x plus 6, that means that the derivative of that quotient is just going to be the derivative of the bottom, or sorry, it's going to be the bottom itself times the derivative of the top minus the derivative of the bottom times the top, all divided by the bottom squared. Okay, so remember the derivative of u over v is going to be v times u prime minus u times v prime over v squared. Okay, so that means our u is x minus 4, and our v is 3 plus 6x. So our v times u prime, well, u is just x minus 4. The derivative of that is 1. Okay, so v times u prime is just 1 times v, which is 3 plus 6x. Okay, so that's our v times u prime. Now we're subtracting u times v prime. Well, u times v prime is just going to be x minus 4, which is our u, times our v prime, which is the derivative of 3 plus 6x, which is 6. So it's going to be minus 6x minus 24. Okay, and that's all being divided by v squared. Okay, so I'm just going to leave this as 3 plus 6x squared. So it's in factored form there. Okay, and just simplifying this a little bit, we're going to get 5x minus 4 over 3 plus 6x to the fourth. And we're going to multiply that by the derivative of x minus 4 over 3 plus 6x. Okay, so that's going to be, let's see here. We got 6x minus 6x on the top here, so that's going to cancel. We got 3 minus negative 24, so that's really going to become a plus. So the top's going to be 27, and we're going to be dividing by 3 plus 6x squared. So this is your solution here. We could expand it, do some manipulation, however we wanted, but that's kind of the main idea. Okay, so that's the chain rule, some intuition behind what the chain rule is, where it comes from, how it's different from, how sine of 2x is different from something like just sine of x, right? We have to treat whatever our inside is like it's just x, and then we have to multiply the whole thing by the derivative of the inside, okay? So it's not a whole lot different from what you already know. We just had that extra piece of multiplying by the derivative of the inside. It's super important when you're doing questions like this to remember that step, or else your question is going to be wrong, right? Okay, so I hope this makes sense, and I'll see you in my next video.